a major contribution to the open source is also the PyMOL wiki, which was started by Jason Retrieve, which is sitting in the back. So a website with lots of information and scripts which you can use in PyMOL. Jason got hired. Jason got hired by Warren in early 2009, and then when Warren passed away, and it was obvious that this good software has to be continued, the good development and the good concept. So Schrodinger acquired PyMOL and Jason kind of in early 2010. And since then continued PyMOL in the very same spirit as Warren did. So this means PyMOL is still open source, licenses haven't changed, and we're really putting a lot of effort in making PyMOL a good science tool. Okay, so what are the strengths of PyMOL? So why do people use it? Of course, high publication quality figures, like the ones that you saw on the journal covers, but also for presentations, PowerPoint slides. Then, because PyMOL is very fast in starting up, very fast in loading structures, changing representations, looking onto details, this makes it so useful for teaching and research. Probably 90% of the times when I fire up PyMOL, this is what I would do, just looking at things, looking at details. PyMOL is cross-platform. It runs on Mac, Linux, Windows. We have now also a mobile version for the iPad and a web plugin version. So you can create a PyMOL session in one machine and easily move the results or the session over to the next machine or send it to a colleague and share the stuff. PyMOL has several methods for structural alignment. This is, of course, again, important for visualization. See how the structures overlay. The more advanced usage of PyMOL is down here. So starting with movie making, you can make animated movies like simple camera motions, zoom up on details, but also object motions or even interpolations, of course, loading trajectories, and then combine all of those. And I will show you examples and a demo later in the session. You can write your own scripts for PyMOL. You won't learn this on the first day, but there are really many users who love exactly this feature, the easy scripting of PyMOL. So you can use Python or a more simplified scripting language which is building into PyMOL. And what I also want to mention is very powerful selection language. If you want to pick specific residues, specific atoms, you just pass the simple selection string when you, for example, want to color all carbons or want to show sticks just for the organic parts or things like that. I want to show you an example movie which combines object motions, camera motions, molecular morphing, and even so-called CGOs. These are compiled graphic objects, which basically means you can not only load molecular data into PyMOL, but with some scripting, you can load arbitrary geometrical objects into PyMOL and complement your scene with those. In this case, it's a simple model of a nuclear pore with a nuclear envelope where this molecule travels through because it's a nuclear transport receptor. And this is a transporter molecule which binds different cargoes That's conformational change upon binding, travels into the nuclear pore, through the nuclear pore, binds to RAMCP in this case, releases the cargo, finds another cargo, travels back. So this was some research at the Max Planck Institute for Development Biology. I was kind of their PyMOL support and their movie maker, but they were really doing nice stuff. Okay, so far for the example. I want to briefly go over the new features that we are working on, or what Schrodinger implemented in the last 2 years. If you have done figures with PyMOL before, you probably know that you would do a ray tracing before saving, so before you put it into your PowerPoint slide, you would do a ray traced version of your figure. And we are working very hard on automating the real-time rendering in a similar quality as the ray tracing. So new technology makes this possible on good graphics card, and we are working on that. We have a new feature called volume rendering for volumetric data like electron density maps or electrostatic maps. I'll show you that in the demo. PyMOL can now load empty stat files, which is very important for crystallographers. We have a new mouse mode for light, so you can have up to 9 lights in PyMOL and easily place them with the mouse in 3D space. For editing operations, we have now a working undo for all editing operations. So this is like cutting out atoms, moving coordinates of atoms, and stuff like that, and also for deleting objects, loading objects. So we have a new plugin manager. That was my PyMOL open source project, and of course we constantly fix bugs. We take this very seriously. Also, in the next release, we will have annotated settings in a graphical dialog. I'll show you this in a minute. And for the ones who like scripting, we have the huge speed up of the iterate and alter commands, who already knows them. So they are used very heavily in scripting, and we could really speed them up a lot. So for the rendering, this is the old style rendering. This is functional to look at, but it's not very beautiful. So we have this simple tone on top of the pig. We have very jagged connections in the joints, and also no anti-aliasing. And in the real-time rendering, we come up with something like this now. You don't even have nice connections, anti-aliasing, nice round tone in the end, but you also have proper light reflection. You can, for example, see we have 3 lights, and this the light is reflected on the sticks. If we go back to the old one, this looks really much different. And on a decent hardware, this is even faster as before. So we use OpenGL shaders for this instead of direct rendering. The volumes representation that I mentioned, this is a classical mesh representation for electron density in this case. This shows you the 1 sigma level of the map data, basically the same as an isosurface. And in our new volume rendering, we can now have a range of sigma values, not only one. This is like continuous isosurfaces with transparency values with different colors. So you can show different sigma levels at the same time. You will also see this in the demo. This is again, volume rendering. In this example, I have a protein complex where one entity has very low or very bad density, probably has low occupancy in this case. So you see the neighboring molecule goes nicely with the 2 sigma level because the yellow color is 2 sigma and the blue color is 1 sigma. So you see here. Sorry. So you see nicely that the one molecule is well defined, and the molecule in the middle is fully defined, but it's still there. And you can show this difference in one picture with volume rendering. And because it's PyMOL, we can also render this into a movie. We would call this a camera motion, so we just change this view and rotate the scene to see from 360 degrees. I mentioned empty set file loading. When you open the empty set, it will show you the volume rendering by default, because that's what we want to push in the future for density representation. And empty set has a couple of settings. You can either pick them yourself, or from the menu use open empty set default to start with the default setting. This is a preview on the next release. Okay, this is a preview on the next release. We already have a dialog which shows the settings of PyMOL. PyMOL has more than 700 settings. This is a lot. This is easy to get lost, but makes it very versatile, so you can tune so many details that you want to change. And what we added now is the panel down here. So we have for, I think right now, 500 out of the 700 have a basic description, like in this case, the cartoon nucleic acid node takes an integer value and you see the different values, what they mean, so that you can quickly pick the right number without going into external documentation, which was there before, but now you have it in the application. And yeah, this panel supports filtering. Also, filtering the help text down here should be straightforward. Then I would like to move to the live demonstration. I will show you volume rendering. I will show how to make a movie. I already found a quite advanced movie which combines object motions, camera motions, and I want to do a molecular morph. Then, yeah, I mean, we had the PyMOL user interface enhancement on the previous slide, but I can show you as well. Yeah, performance and rendering, of course. Yeah. So, oops, I switch now. So somehow my presentation. Just a second. So I want to start with the volume rendering, and I put together a PyMOL session, which I guess a different PyMOL. I put together a PyMOL session which reviews the different methods. Oh no, I have two. Soon you don't have any. Still loading. So, yeah, which reviews the different versions how to visualize map data. So in this case, it's an electrostatic map. I calculated that with ABPS. It's an RNA molecule. In principle, the color is ranged from -5 to 5, blue to red, equally. But because the RNA molecule is so negatively charged, we don't see any blue color in the example. And the typical representation so far is that you map the values onto the molecular surface and have the color gradient there. Oops, sorry, I shouldn't walk. Yeah. Can't get rid of this. Okay. So the next typical representation. Next typical representation or isosurfaces. It's basically the same as an isomesh, so you have one particular sigma level, where you draw a surface or a mesh. This has a quite solid appearance, although map density is not solid. Its range is in 3D space, which this representation fails to show, in my opinion. We have another, maybe less common representation, which is the so-called slice. Here you cut through the map. Again, have the color gradient, in this case on this plane. You already see we now have the gradient. Come on, you have to stay close to the microphone. I'm getting nothing. Okay. Sorry, I'm used to walking to the screen. Okay, so you already see the gradient on the plane, but you have to rotate to get the data in each direction. So the new volume rendering kind of combines features of both. It is the gradient in 3D space. It is transparent, so it doesn't look as solid as the isosurface. Let me show this. So in comparison, isosurface looks quite solid. The volume representation shows that it's really ranging in 3D space. Okay, this was an electrostatic example. Let's pick another one. For example, density from cryo-electron microscopy. So this is an EM map. By default, PyMOL just shows the extent of the map, and we go for a default volume representation. To now pick your color values and transparency values, you would switch to the external window, and we have a volume panel there. It shows you the histogram of the map data, and I will start with some peak where I see some density here. Take a color. I can make this opaque like an isosurface if I move this to the top, or I can make it transparent and then pick another sigma value, have it in a different color, and you already see it starts to show me different features which are related to density. I can slide into this, and if I make this a bit smaller, start to see that if I adjust this further, how the density is is organized in this. It's a virus or a lambda phage. We can even see into this channel. If I remove again the red color, I can look into the channel kind of. And like this, it might suggest there is no density, but because we can place with some transparency color everywhere, we can really visualize this better than with just an isosurface, for example. And also on the surface, you see there are like blobs coming up, which probably correspond to single proteins. If we fetch some normal sized protein, you will see the size of a protein would something fit into here. But PyMOL easily handles objects of any size. And of course, electron density goes on the same line. So this is the classical mesh representation of the electron density, and I can show you. If you have a close look, this is the 1 sigma mesh, and I put the volume also exactly on 1 sigma first, but in addition, I choose yellow for the 2 sigma. I'm sharing my desktop with them. So I have several sigma values, and if I remove the mesh, you still have the 1 sigma nicely outlined by the blue color, but also see where regions of low density are and where regions of nicely defined protein are. And as a last example, I will show you that it doesn't need to be molecular data at all, of course. So here we go. Show the volume. So what's that? And what kind of density features could a tooth have? Just start putting in the high density range some color. Suddenly see there's at the top a very high density region coming up, which must be really hard. So we learn now that's the dentin. And you can also see, because this is all transparent, so we can vary the transparency. We can again see how far the underlying density features reach, where the high density starts. So you can easily explore by putting the colors into the volume editor. You can really explore the map in 3D. So that's for volume rendering. Let's move on to movie making. And so I would like to make a movie with a molecular morph and object motions and camera motions. So my favorite morph is adenylate kinase. I will always, so in this case I would start fetching PDB structures. It's an open and a closed conformation. Maybe let's get rid of the water. And for morphing, we would need to superimpose them first, otherwise it would morph from left to right, which is obviously not what we want. So I just align the two. And so far, you need to run a script to do morphing, but in the next release of PyMOL, we will make this much more simple, available from the generate menu. Oops, there is we will put the morphing in the generate menu of the object. Will run for a couple of moments. This will run a second program which is called PyMOL. It will do some refinement on sidechain atoms to not get distorted intermediates, and will give us a default trajectory of 30 frames. So here we go. So we now have 30 frames. It's by default starts to loop through them, but I don't want this default movie. Stop this. And I would like to start, or actually I want the ligand, which is in this structure. So I would extract that to its own object. No, it didn't do this. Again. So here we go. Show the sticks for the organic compound, which is the ligand, and I only want the ligand, so I remove what's not organic. So now I have the ligand in its own object, and I can drag that around for movie making purposes. But let's start with a camera motion. So we can start from the movie menu. We have a program called camera loop, and this would be a Y roll. Let's do 40 seconds. The simple camera rotation. For the morphing, I would append some states, like 4 seconds, so that in the end I get a movie which does nothing for now, but we can now continue from here. So I would store the ligand, switch to the motions menu. I store that and drag it out to something like here. So now I will interpolate the movement of the ligand, and I also want to open up the structure. So I store the state 1 here, and something like here, the open state. So now I will automatically interpolate this so that I start from the beginning. Oh, I need to store the state 1 also in the beginning. So there we go. And we have the camera motion, morphing, and object motion. And actually, I would need to store the end frame correctly now, but you get the idea. You don't need scripting for this, so this is all done with the 3-button motions menu and the mouse and the movie panel. So making movies in PyMOL is not that hard. Okay, then let's go to the 3-button lights mode. You can use the same protein again, and we have a new mouse mode called 3-button lights, where you can easily track the direction of the light and place it where you want it. So previously, you could also place the light, but you had to give it a 3D vector on the command line and go back and forth for placing it. Now you just take your mouse and move your light around. And you can have up to 9 lights and place them all individually. I see we are getting close to 2 o'clock, and we wanted to do a question and answer session. So I would say I'd stop here and to ask questions, and I'm happy to answer them. Yeah. So we will have the alpha release in like 6 weeks. That's our plan.
Is now 1.6 or what?
So the current version is 1.5.05, and what I showed you was 1.6. So our current development version. Okay. Yeah.
There are two ways to convert PSE file.
I mean, a PDB file doesn't hold all the information, which is a PSE file. But if you yeah, so you just want the structure which is in the PSE file as a PDB file. So you just load it in.
Because I cannot open the PSE file, WordPad or
you can open the PSE file with PyMOL and then save a PDB file. You just yeah, sure. So let me use this one. So I open that with PyMOL. I have a structure in here. It's this one, and I just do file, save molecule, and I can save it as a PDB file. So it's this one. I pick a file name, save it. Other questions?
So I have a question from the audience. If there is a wiki page with the information how to make a movie working.
Yeah, there is. So I have internet. So as I said, this will be much more easy in the next release because you put it in the menu. It will automatically align the atoms. Because for morphing, of course, if you have 2 input structures, it's crucial that they have exactly the same topology. And often people use similar structures which are not identical, but we do this by internal alignment and matching, and this is then all done from the menu. So far, if you want to do morphing, you have to do this yourself. But if you just Google for PyMOL wiki morph, it will bring you to an example. So copy pasting this should work straight away with the current PyMOL release. Maybe I should add the underlying reachMOL application is an incentive PyMOL product. So this will not run on the open source version. Most other stuff will, that I showed you, but not reachMOL.
And all the big numbers have access to incentive already.
Yeah. So it's not a problem for you. Yeah.
It shouldn't be your boundary, or because you showed two structures, right?
Yeah.
And the boundaries for two structures were exactly the same, or there was some missing part in one structure, and so because
Yeah, so that's
exactly the same.
I mean, you're moving an atom, so it must be there in the beginning and in the end.
Okay.
That's obvious, yeah?
Yeah.
So,
Come on, you can repeat the question.
okay. So the question is, I think, what's the problem, or what happens if there's an atom missing in one structure?
Yeah, right.
Yeah. So, if you look at this script, it starts with an alignment. And after alignment, I know exactly which atom is in those structures. It's a sequence alignment, expands to all atoms of the same atom name, atom type, and that I take as input for the morphing. And the ones which are not in alignment, I will drop. Yeah. 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 So Jason wants to see a structural alignment and want to save the alignment to a cluster W file. So can I just use the one? No, let me take some homologous structures. I hope I can touch them now. Okay. Let me get rid of the chains that I do not want. And here. Okay. So these are low sequence identity, and I would, for example, start aligning them from the menu, and I get a aligned object which appears in the object menu panel. And this is first, if you zoom in, you will see which atoms are matched by the yellow lines which connect the atoms. Also, if you enable the sequence viewer, you will see the alignment. So you see the gaps and the non-aligned atoms. And this alignment I can now save to a file. It's actually not a molecule, but you pick the alignment object, pick a file name, but I would save this to and oops. Maybe my development version messed this up. But it should save a cluster W file, so a simple text file with the alignment. Let's try this. So I saved it now from the command line, and if you look, there it is. So this is what I just said. Okay, other questions? Yeah, sure. But these have only 28% sequence identity. They have many gaps. The morphing will look crappy. I mean, it's a natural problem. You can't move an apple to something, so a banana.
Okay. Any further questions? That's all. I don't have any. 1 second.
Yeah.
It's cluster W.
Cluster W on is it in the open source version?
Yes. I think apart from PyMOL, everything which I showed you is in the open source.
Okay, so
Thank you very much. And great presentation. We'll finish the WebEx part right now. We'll have a short break, and then we're going to go to the tutorial sessions. And this is going to be available. I think we'll have to check if the recording worked properly, but we're planning to put it online as well for people who attend it.
Could you give a short explanation? What difference to different classes?
Well, the first introductory class is for people that haven't really used PyMOL extensively or at all, and that's in the library. If you've been using PyMOL for several years right now, you've made figures with PyMOL in past, you're probably encouraged to go to the second session. We'll be learning how to make movies with PyMOL. So it'll be a bit more advanced class. And they about the walk between two sessions is about 10 minutes. So if you end up in the wrong class, it might be difficult to move down. But we'll stick around for a couple more minutes, and if you guys have specific questions about each session, you can talk to the instructor. So Thomas is going to do the introductory class in the library, right? And Jason is going to do the movie making class. He's sitting in the back, so you can talk to both of them right now to get a little bit more information. If you're not sure of your level, if you're on the right level for the tutorials. And everybody got the instructions online how to download PyMOL. You have laptops and you download the tutorial session files, right? We shall send this information. If you didn't do it, the download itself takes a couple minutes, so you still should have enough time to get ready. All right?
You can use half past. Yeah.
Right.
Yeah. Yeah. Yes.
With protein,
You didn't know.
so experimental.
Yeah.
So just change the location of one domain to another protein.
I think we just need
So you have two different setups. So the mutant was a mutation. So you need to pick
since I don't have structure,
I don't have structured data. You want to show both
you solved it okay, right?